Hello everyone. Today we will discuss quantum mechanics and applications. In this lecture video we have splitted the whole quantum mechanics and application in three parts. In first part we will cover the classical versus quantum physics, and the next de Broglie hypothesis, from where the main foundation of the quantum physics start, that matter, wave and characteristics. Then we will discuss about experimental study of matter waves, and then Heisenberg uncertainty principles. And part 2 will be discuss about wave mechanics, basics postulates of wave mechanics, Schrödinger equation and its steady state form, and properties of the wave function. And part third, the application part, we will discuss about one of the simple applications of Schrödinger equation, the particle in a box infinite square well potential. So let's start with the first unit. It will cover the following topics, with starting with from quantum physics, and then we will discuss the de Broglie hypothesis, matter wave and its characteristics, and then experimental studies on matter wave, and then finally we will be discuss about the Heisenberg uncertainty principle. So first is classical physics. What are the limitation of the classical physics? What is the main? What are the things we discuss in the classical physics? Actually, the classical physics provides the foundation for understanding many physical phenomena at macroscopic scale. So basically, classical physics gives the description of the system in macroscopic systems like planets, projectiles. So it accurately describes the motion of the planet, the behavior of the projectile, and the other systems which are visible to eye in naked eye. The classical physics operates under the assumption that if the initial conditions like position, velocity, etc., of any system are known, its motion of planet can be precisely predict, or we can say that we can accurately predict. So like example, the trajectory of projectile or orbit of a planet. So we know that foundation theory of classical physics is based on Newton's laws of motion govern the dynamics of the objects under force. We know from Newton's law, the force is equal to nothing but the product of mass and the acceleration. Uh, F is equal to m into a, and then the based on the Newton's law, the Lagrangian and Hamiltonian formalism uh, can be formulated, and key system that harmonic oscillator planetary motions can be described, and that in Hamiltonian mechanics, basically the further abstraction central to the modern physics, especially in transition to quantum mechanics. And what are the failures of the classical physics? Actually, as physics progressed into the microscopic domain, several experimental observations could not explain with the classical theory. So, stability of the atoms, classical electrodynamics suggest that orbital electrons should continuously radiate energy and spiral into the nucleus. However, atoms are stable. Hydrogen spectrum, the classical physics predicts a continuous spectra, but hydrogen emits, we know, the discrete spectral lines. So basically these discretens the this implied quantization beyond classical expectation. So, and also photoelectric effect, that classical physics predicts that light light's energy build up over times regardless of frequency. Experimentally it observed that electrons are emitted instantaneously. Emission only occur when there have some sufficient frequency or threshold frequency. And classical physics basically don't explain the stability of the atoms, so could not explain why electrons do not spiral into the nucleus. Hydrogen spectra could not explain discrete lines. Photoelectric effect predicted gradual energy build-up, contradiction of experimental results. Compton effect and blackbody radiation were inconsistent with the classical theory. So, classical physics could not explain several atomic, or we can say that atomic and several quantum phenomenon is not explained. So, we need for a new framework where we can explain those experimental or microscopic level phenomenon. So the consistent failures of classical physics in the atomic and subatomic realms pave the way for quantum mechanics or quantum physics. It is a basically revolutionary framework that incorporates probabilistic intercorrelations and quantized energy level. In the upcoming in this series lecture, we'll explore that how quantum theory emerged to resolve this contradiction and how it reshapes our understanding of physical reality. So first we'll discuss about the atomic stability problem. So from uh, prediction, we according to classical electromagnetic theory, that any charged particle in motion, like an electron orbiting in a nucleus, should continuously radiate energy. So this is our classical electromagnetic theory prediction, that electrons radiate energy continuously. So in this view, electrons spiral inwards as they lose energy. Atoms should collapse in an extremely short time. The time limit may be kind of very less, maybe 10 power of minus 11 second. And this prediction arises from applying Maxwell's equation to the atomic level. So this consequence give that orbital decay and the atom collapse, and basically electrons lose the kinetic energy. Eventually electron would fall into the nucleus, and this implies atom cannot exist in a stable form, yet we know they do. So this contradicts also uh, this contradiction shows a breakdown of classical physics at the atomic scale. So real observation is come to us that atoms are remarkably stable. Matter around us does not collapse, and spectral lines of electron like hydrogen are discrete, not continuous. So this discrepancy between prediction and observation highlighted the limitation of classical physics and led to the birth of quantum theory. So transition to quantum mechanics is now introduced, that Bohr models introduce quantized orbit. Later Schrodinger wave mechanics provided more accurate explanation. So these models restrict the energies states of electrons, ensuring the atom do not radiate energy continuously in stable orbit. So we can say that the atomic stability problem is a classical example of how empirical observation can challenge well-established theory, promoting revolutionary advances in physics. It demonstrates the need to move beyond classical frameworks and embrace quantum mechanics to understand the microscopic world. So now we'll discuss that atoms and failures of stability of the atom. That this is the here we can see that according to that electron moving in a circular orbit around the nucleus is undergoing acceleration. So when it will be accelerate, the accelerated charges radiate energy continuously, as we mentioned as per Maxwell equation. Then if they accelerate charge back, radiate energy continuously, and then this means the electron should spiral inwards like this, but this is wrong, as this is wrong. If class Now we'll explore hydrogen line spectral mystery. So basically, this is one of fundamental mystery that challenged classical physics and paved the way for quantum uh, theory, the hydrogen line spectra. Despite being a simplest atom, hydrogen expose deep flows in classical physics. So first, what is hydrogen line spectra? Basically, when hydrogen gas is excited by electric discharge, and its emit light is passed through a prism, distinct spectral line appear. So uh, basically we can see that these kind of lines we can see like Lyman series, that is ultraviolet, Balmer series visible region, then Passon bracket refined, that are infrared region. So basically only a certain wavelength of light are emitted, a discrete spectrum but continuous. So we can see here a range of this spectrum, and it is like discrete spectra, not the continuous of like classical. So basically in the classical physics we can predict about continuous spectra like this, no discrete line, but experimental reality tells about the distinct emission lines, and so here quantum explanation required. So this explanation can get properly from the quantum physics or quantum mechanics. So basically this is the Richenberg formula of wave number nu bar is equal to r, that is just constant, and in within bracket 1 by n2 square minus 1 by n1 square. This n1 and n2 different level, different energy level. So this formula actually accurately predict the spectral line of hydrogen, but at the time it had no theoretical basis. It was just a feed to all the data. So why this mystery, like what determines this quantized energy levels? So why does hydrogen, like just one proton and electron, emit light only at a specific frequency? What does imply about energy within atom? So this question leads us to know or explore about Bohr's quantum model development of quantum mechanics. So we can conclude that hydrogen line spectrum posed a profound challenge to classical physics. It hinted a hidden structure within atoms, one governed not only by continuous variable but discrete energy levels, Understanding this mystery mark the beginning of quantum revolution. Now we'll discuss about the photoelectric failure. That what is photoelectric effect? That when light actually shines on a metal surface, electrons are ejected from it. This so it is nothing but about emission of electron from a metal plate when illuminated by light or any other radiation of suitable wavelength. So these emitted electrons are the electrons which are emitting, these emitted electrons are called the photoelectron, and the phenomenon is observed with observed basically the in UV visible and also infrared light depending on the material. And classical prediction is that energy of light depends on intensity, not frequency. A more intense beam should provide enough energy to eventually eject electrons regardless of frequency. This should be a time delay of low intensity light before electrons are emitted, and all frequency of light should eventually eject electron of if intensity of high intensity is high enough. But experimentally observed is something different, like so classical observation is that electrons emission depends on light intensity, but observation out emission depends on the light frequency. So experimental observation is first is the threshold frequency. What is that? It is basically that no electron are emit below a certain frequency, no matter the intensity. And instant emission, that electrons are ejected immediately when above threshold light strikes the surface, no time delay. And kinetic energy depends on the kinetic so kinetic energy basically will depends on the frequency, not intensity. More intensity above threshold, more electron, not more energy per electrons. Number of electrons will be increased while increase the intensity. So about photoelectric effect, in this my previous lecture, in this link have the details about photoelectric effect equations and all. So this photoelectric effect results directly contradiction of the classical prediction. So in 1905, scientist Einstein first observed. He observed in that light consists of discrete packets called the photons, and also the experimental result disagreed the classical physics or classical electromagnetics, which predicts the continuous light wave transfer energy to electron, which uh, would uh, would then be emitted when they accumulated enough energy. So this is the one contradiction. And second is an alternate in the intensity of the light would theoretically change the kinetic energy of the emitted electrons with sufficiently dim light, resulting a delay emission. And also this quantum theory explanation is that the electrons are dislodged only when incident light or radiation photon frequency exceeds a certain frequency called the threshold frequency, regardless of the duration of the expose. So based on based on this observation of the uh, quantum physics or Einstein's this observation. It's need that quantum explanation needed, and which matches actually quantum explanation with the experimental result. So now will we move to Compton effect discrepancy. So what is the Compton effect? Basically, the Compton effect is a phenomena that further confirm the particle nature of light and solidify the foundation of quantum physics. So basically we can see that Compton effect is when a beam of X-ray was scattered by material. The scattered radiation considered two components of X-rays, one with the same wavelength and another with the longer wavelength. So basically if we go back to classical expectation of this, that we know that according to classical wave theory, that X-ray scattering of electron should only result in redistribution of intensity, and there will be no change of wavelength or energy. But experimental source which get verified by experimentally, it's different than this classical observation. So it shows that this effect will have two component of the X-ray. One is same wavelength, another is longer wavelength. And from here, that Compton found that he first directed the X-ray into a graphite target, and then observed this scattered X-ray using a spectrometer. This scattered X-ray had a longer wavelength as well as the same wavelength, and this contradicted the classical electromagnetic theory. So here the quantum explanation is so this too is the contradiction of the classical mechanics and the quantum explanation. And so classical prediction is that no major difference is no change in the wavelength in post scattering. Experimental result shows that wavelength increases after the scattering. So significant is photon momentum quantization. This. So basically, since we are getting to different wavelength, then the scattered photon have lower energy, hence the longer wavelength, and electron recoil with the kinetic energy. And this Compton shift basically can explain from this Compton basically this explain from the quantum that wavelength, that formula, that it is basically the that formula is delta lambda, that delta lambda is basically that lambda dash minus lambda, this change of the wavelength is basically depends on h by m naught c. H is the Planck's constant, m naught is the rest mass, c is the velocity of light, to 1 minus cos of theta. So this angle of scattered angle is influence, or scattering angle is depends on this Compton shift. So this shift is independent of the intensity and confirm me the particle behavior. So significance we can identify from Compton effect, that it provide the direct evidence for photon carrying momentum, reinforce the Einstein's photon theory, and classical wave theory failed to account the wavelength shift, supported the duality of the light, both wave and particle. So we can conclude here that Compton effect was another nail in the coffin for classical electromagnetism, and that it proved the light cannot fully described as a wave, and that quantum mechanics is essential here to understand the microscopic phenomenon. Now we'll move another drawbacks of failure of the classical physics that are known as black body radiation. So a black body is an ideal object. A black body is an ideal object that observe everything, means all incident radiation, and emit radiation at a characteristic spectrum depending only its temperature. So example, like a furnace cavity, the sun, and the heated metals. So classical prediction is Rayleigh-Jean's law is that according to classical physics, the energy radiated per volume at a frequency at a particular frequency increases with the wavelength, and at a high frequency this leads to infinite energy, a paradox called the ultraviolet Castrol field. So at high frequency this leads to infinite energy, a paradox called as ultraviolet catastrophe field. So basically energy, classical prediction is infinite energy at short wavelength, and energy peaks and energy will be reaches to this peak point, and then it will be come back. And resolution is the quantum energies quantized concept. So ideal black body at thermal equilibrium will emit radiation in all frequency range, it emitting more energy as the frequency increases. This contradicts the experimental observation. And here come the Max Planck quantum theory that matter composed of large number of oscillating particle, energy of oscillating particle must be quantized. So basically the idea of Planck's hypothesis is that energy is not continuous, it is quantized, emitted or absorbed in discrete packet, or we can say quanta. Each quantum energy each quantum has energy, and this energy E is equal to basically h nu, where h is the Planck's constant, nu is the frequency of radiation. And he introduced that total energy variation, that E and nu d nu is equal to some constant like 8 pi h nu q by cq multiply with 1 by e to the power h nu by kt minus 1 into d nu. So these match actually with the experimental result perfectly, and especially explain the drop off at high frequency. So basically this result first introduce the concept of energy quantization, challenge the continuous energy assumption of classical physics. Planck's constant h became a fundamental constant in quantum theory, and this led to the groundwork for the Einstein photon theory and quantum mechanics. So basically the classical physics, this if we summarize this classical physics limitation, that major five key failure is that classical physics fails to explain that atomic stable explanation, hydrogen line spectra, photoelectric effect, Compton scattering, black body radiation. So here to overcome this, it come to the de Broglie hypothesis matter wave. So in the next step of physics is First is quantum physics. It introduced the quantized energy state. In second, wave particle duality, that particles behave like waves. And third, quantum electrodynamics. It describes the interaction of light and matter. So basically now we will explore the revolutionary concept of quantum physics, so called the de Broglie hypothesis. So this basically introduced the idea that particle exhibit wave like behavior, and this concept forms the foundation of wave mechanics and quantum theory. So just for a overview, that classical physics, that in classical physics the particles like electrons and waves like light are separate, but quantum discovery said that light behaves both as wave and particles. Photoelectric effect, Compton effect is the proof. And de Broglie asked if he asked a question that if light can act as a particle, can matter act like a wave? So here it came the picture de Broglie hypothesis in 1924. So 1924 the Louis de Broglie introduced the revolutionary idea of wave particle duality, and he proposed that any moving particle has a wavelength associated with it known as the de Broglie wavelength. So this idea is the bridged the gap between classical particle and wave views of nature. So basically de Broglie wavelength is associated with any moving particle, and that Planck's constant h, lambda is equal to Planck's constant h divided by p. Basically lambda is equal to h by p. And example are electrons like ultra small wavelength, important in quantum scale, baseball and car wavelength too tiny to detect. So and the major implementation of matter wave is like that microscopic particles like electron have noticeable wavelength. For macroscopic object, the wavelength is so small it is undetectable. So basically if we look here, that this perspective is first is the wave, matter wave. In matter wave, no traditional wave but probability waves describing behavior. Complementarities, particle source wave or particle trail, never both simultaneously. And quantum mechanics unified the theory across explaining the matter's dual nature. So basically if we see that, suppose here how we'll find out this, suppose that we know that electron mass electron suppose we know the electron mass, that electron mass is 9.1 into 10 power of minus 31 kg, and velocity is 10 power 6 meter per second. And now if we want to calculate this with the formula lambda is equal to h by p, we know the Planck's constant, and p is nothing but the mv, it is momentum. So if we use these two formula and Planck's constant h we know, then we can got is approximately value 0.73 nanometer. So this is basically this value is comparable to the atomic dimension. So says in so now the properties of matter waves. First, that lighter the particle, greater is the wavelength, and smaller the velocity, greater the wavelength. For nu equal to 0, lambda is infinity. That means only moving particle matter wave is associated. Whether the particle is charged or not, matter wave is associated with it. These waves are not electromagnetic but a new kind of waves. Velocity of matter wave depends on the velocity of material particle. It is not the constant, and the velocity of matter waves is greater than the velocity of light. The wave and particle aspects of moving particle can never appear together in same experiment, and wave nature of matter introduce an uncertainty in location of the position of the particle. Wave cannot be said exactly at the point or exactly at same point. So now it is needed that experimental verification of this matter wave or de Broglie hypothesis. So basically de Broglie hypothesis, there are major three experiments are that Davis-Jarmar experiment. It confirmed the electron diffract like waves in 1927. Thomas thin film diffraction. It shows the electron interference pattern through the thin film. And impact, it's laid foundation of the electron microscopy by proving wave nature. So we will discuss in details about the this Davis and Jarmar experiment. What is this actually in this experiment? So before going to that Davis and Jarmar experiment, let us just evaluate the de Broglie wavelength in different form. So basically de Broglie wavelength, if you want to find out in terms of kinetic energy, so basically we know that de Broglie wavelength lambda is equal to h by p, and we know the momentum of if the light of frequency velocity is frequency is nu, then the momentum p is equal to basically h nu divided by c. C is the velocity of light, and since from de Broglie wavelength we know lambda is equal to h by p, then we can easily write this lambda formula. Lambda is equal to h by mv, and then this is basically h by mv, and we know the kinetic p is equal to, you know, the kinetic energy k is equal to half of mv square, or equal to p square. This mv basically we can write this p square by 2m. So p is nothing but root over of twice m, and if this is the kinetic energy k, or we can write the ek. So this is basically the ek, and if we put this, we can get this lambda is equal to h by under root over twice me, and is the kinetic energy of the moving particle. So now if we want to calculate the de Broglie wavelength associated with electron, lambda is equal to h by twice mev. So where this m is equal to rest mass of electron, E is the charge of electron, and capital V is the accelerating voltage or potential. So we know this is the lambda is the constant, m and E, if we put the value, we can get, once can get this lambda is equal to 12.26 divided by root over capital V. So this capital V is basically the accelerated voltage or the potential. So if we know any of the system, the accelerated voltage or the potential, one can easily find out the value of lambda. So now we'll come to the Davis-Jarmar experiment. So basically in this experiment is established in 1927. He proposed that electron scattered from a nickel crystal produced diffraction patterns, a wave phenomenon. So this confirm wave nature of electrons. And electron diffraction in gas and solid reinforce wave behavior of matter. So importance in quantum mechanics is that it introduced the wave particle duality of matter, laid the foundation for Schrödinger wave equation, and it is essential in quantum confinement, electron microscopy, quantum walls, and semiconductor physics. So basically in this experiment, Davis and Jarmar, he basically set that verify the electron diffraction on crystal and probe the evidence for matter wave. So this setup, this is the full setup of this Davis and Jar experiment. So first he actually said the electron are produced by heating of filament by a low tension battery, and then the electron are then accelerated through a potential difference V in electron gun. This electron beam falls a large, this electron beams will falls a large, this is the incident beam is coming, this is the direction of incident beam, it is coming in a large piece of crystal, and this crystal is made up with the nickel. The electrons are scattered in all directions by atoms in the crystal, and the detector can be moved to any of angle phi relative to the incident beam, and the energy of this electron in this primary beam is actually the angle at which they reach the target, and the position of the detector, this angle basically, and this position of this detector could be all be verified. So basically here he want to set that in the experimental procedures he actually used the accelerated potential V is given at very low value, and the beam of electron normally falls on the surface of the crystal, second, and third the detector is moved to various positions, like this is incident boom, and this angle basically can vary at and different position, this value will be noted, and then the intensity of the diffracted this beam will be plotted against incident beam, and this beam entering the detector. The method of plotting is such that the intensity at any angle is proportional to the distance of the curve at angle from point of scattering, and this observation he shown repeated for different accelerating voltage, like that incident beam, and this at different voltage plotting, and this with changing different accelerated voltage and number of graphs as drawn here. We have shown 40 volt, 44, 48, 54, 60, 64. We can see that this basically notably change in this part, this car position. So this shows a topically polar graph of the electron intensity, Actually, the graph remains fairly smooth till the oscillating voltage from become the 44, and when a bump appears at the curve, we can see here that a bump is appearing at 44, and the bump becomes most prominent in the curve when the this voltage is above 50, or we can say that at 54 this is here it is come noticeably more prominent, and as the oscillating voltage is further increasing, we can see from 64, 60, 60, 64 and 68, the bump decreases in the length, and finally it is disappearing this part if we compare that at 68 volt. So this observation and this from this plot actually calculated the observed wavelength. So basically for so which we was plotting there, that at 54 electron volt this beam position. So for nickel we know that d spacing of atomic spacing is d is equal to 0.091 nanometer, and this is measured from the X-ray diffraction, and we can see that this intense reflection of the beam at an angle phi is equal to 50, and we know from the de Broglie's equation that n lambda is equal to 2d sine theta. So here for n is the 1. If n is 1, then de Broglie wavelength, if we use this formula, we can find out lambda is equal to this 0.01 0.165 nanometer. And now interesting thing is that if we know that electron kinetic energy, the electron kinetic energy that at 54 volt, and then electron wavelength is this 0.16 nanometer using this formula. So and that yeah, from using this experiment calculated the de Broglie wavelength lambda this, and then the using this electrons kinetic energy at 54 electron volt, the electron wavelength is therefore we are getting 0.0166 nanometer. If we look at these two values, so this observation proves, or these observations agrees well with the expected wavelength, and the Davis-Germard experiment that directly verified de Broglie's hypothesis of the wave nature of moving bodies. So basically this electron wavelength has calculated from different with considering the different angle and the surface, it is found that this wavelength values is the very similar. So this is the direct proof of the de Broglie hypothesis. So if we summarize, the de Broglie proposed that all matter has wave-like properties. His hypothesis united particles and wave behavior under a single framework, and it is experimentally verified and transformed our understanding of microscopic world. So de Broglie hypothesis revealed that nature is fundamentally dualistic, matter and energy. So both particle and wave behavior depending on how we observe them. So this application of this is electron microscopy, high resolution via electron wavelength smaller than light, neutron diffraction, wave nature of neutrons, aid material structure analyze, quantum computing. It explored the quantum wave properties for computation, and its resolution formula, this d is 0.61 lambda, defines the resolving power based on the wavelength and optics. So now we will discuss the Heisenberg uncertainty principle. So Heisenberg uncertainty principle, it basically states that the it is impossible to determine precisely and simultaneously the value of both the members of a pair of physical variables which describes motion of an atomic systems. So to explain this Heisenberg uncertainty principle, basically if we just let us consider that probability of uncertainty in position and the momentum. So basically this pair of physical variable is called before that just see that what is called this pair of physical variables. These physical variables basically called the canonically conjugate variable. So if we want to measure the position and momentum simultaneously, then what error we'll get and how from this principle. Let us see that example delta x into delta p, that will get lambda divided by 2 pi. So according to the Heisenberg uncertainty principle, that position and momentum of a particle, so suppose the electron, that position x and momentum is p for electron, that both these parameter cannot determine simultaneously to any desired degree of accuracy. So basically if we take that delta x is the error of measuring the position, then and delta p is the error in determining the momentum at same instant. So these quantities are related like this measurement, this error. So basically now if we look that the product of the two errors is approximately the order of Planck's constant. If delta x is the small, if delta x is small, then delta p will be larger and vice versa. So it means actually that if any quantity is measured accurately and the order of quantity becomes less accurate, or thus any instrument cannot measure the quantity more accurately than predicted by this Heisenberg uncertainty principle. The same relation holds for the energy and time to any of the given event. Suppose delta E is the error in energy measurement and delta T is the error in the time measurement. So this quantity will be equal to h by 2 pi. Yes, this is the formula for energy with time. So according to actually the classical ideas, it is impossible for a particle to occupy a fixed position and have a definite as a finite momentum, and we can predict exactly its position and momentum at any time later. But according to the uncertainty principle, it is not possible to determine accurately the simultaneous value of the position and momentum of the particle at any time. Heisenberg uncertainty principle implies that in physical measurement, the probability takes the place of exactness, and as such phenomenon which are impossible according to classical ideas may find a small but finite probability of occurrence. So this this shows that the physical measurement probability takes place of exactness, and as such phenomenon which are impossible according to classical ideas may find a small but finite probability of occurrence. So now the two illustration of this Heisenberg uncertainty principle. So in this experiment actually shown that suppose we try to measure the position and the linear momentum of an electron using a imaginary microscope with very high resolving power as shown in this diagram. So the electron can be observed if at least one photon is scattered by it into the microscope lens. Here is the microscope object and this as the direction of the photon, and here the electron. So the resolving power of microscope is the given by the relation, that is nothing but delta x is equal to lambda divided by 2 sine of theta. Here this delta x is the distance between 2 points at which can be just resolved by microscope, and this is the range in which the electron would be visible when disturbed by the photon. Hence delta x is the uncertainty involving in this position measurement of the electron. However, the incoming this photon, this incoming photon will interact with the electron through the Compton effect. So to be able to see this electron, that the scattered photon should enter the microscope within the angle of this 2 theta. So if so, the momentum impact by the photon to the electron during this impact is of the order of h by lambda. So this component of the momentum along in this direction OA basically will be h by it will be basically in this direction it will be basically minus it will be basically minus h by so delta x is equal to h by 2 lambda by 2 sine theta. Now this momentum component in along this OA, this direction is equal to minus h by lambda into sine of theta in this OA direction, and this same value will be along OB direction. It will be h by lambda sine of theta. This momentum component along this OA direction is this, and hence the uncertainty of the momentum in x direction is just nothing but will be just delta px is equal to h by lambda sine of theta minus of h by p sine of theta. So this will be equal to twice of h by lambda into sine of theta. And if we now find out that delta x into delta p, delta x and delta p, so we can find out that from that we can find out from this determination of the position by X-ray, that delta x and delta px is nothing but is basically if we say that delta x into delta px is equal to h, or we can write it getter equal to h by 2 pi. So this a more sophisticated approach is this delta x delta px less getter equal h by 2 pi. So it is clearly says that the process of measurement itself that perturbs the particle whose properties are being measured. And second experiment is shown with that diffraction of beam by electron by a slit. So basically here it is given a we can say that screen, and here that beam of light is coming, and by passing through this slit it can with changing this diffraction angle or setting this diffraction angle can be project on the screen, and you can find it like this spectrum. We can find out like that spectrum. So basically here a beam of electron is transmitted through a sheet and received by a photography plate P, or we can say this is the screen at some distance from the slit. So we can say here only that the electron must have passed through the slit and cannot specify its exact location in the sheet as the electron cross, and hence the position of any of the electrons recorded the plate is uncertain by a certain amount of equal to the width of the slit, let us say delta y. And now if we say that wavelength is the lambda of the electron and theta is the angle of deviation corresponding to its first minima, this lambda. Okay, so from the theory of the diffraction, this delta y can be is equal to lambda divided by sine of theta, and this is the uncertainty in determining the position of the electron along the y-axis. So same way actually if we look that initially the electrons are moving along the x-axis, and so the theory have no component of momentum along the y-axis. As the electron are deviated on the slit at initial path from the pattern, they acquire an additional component of momentum along y-axis. And if p is the momentum of the electron on emerging from the slit, then actually we can say that component of the momentum in y-axis will be the means delta py will be equal to 2p sine theta. So that is 2p sine theta. So that is equal to, since lambda is equal to h by p, we can write it 2h by lambda sine of theta. So this is the value of delta py, and here we have find out the delta y is equal to lambda divided by sine of theta. So once can multiply with delta y into delta px, and then can find out is equal to 2h. So or we can write it in this way that delta y into delta py getter equal h by 2 pi. So this is the basically the Heisenberg uncertainty principle. So so if once know the parameters of error in one, another parameter can be like if we know the error in the parameter of position, we can find out the error in measuring the momentum like using this formula. So this hence it is proved that Heisenberg uncertainty principles. So now we will discuss a bit about the wave mechanical atom, that from these principles. The most recent development, actually the most recent development in the theory of atomic structure shows that the Bohr picture of atom with sharply defined electron orbit is not correct. According to the wave mechanics, actually that wave mechanics developed by Heisenberg, that Schrödinger and Dirac, that electrons move around the nucleus as a wave packet, which forms is somewhat similar manner as like standing waves are formed in sound. So the atom model has electrons in basically that atom model has electron in various orbits, and electron becomes a matter of wavelength lambda. So basically this lambda is equal to h by mv, and this electron exists as a standing wave in each orbit. So energy level and orbit of the Bohr model actually are retained. So even the quantum conditions of Bohr follows the wave mechanics. For example, consider an electron in hydrogen atom in a standing wave extending in a circle around the nucleus like that, and in order that the wave must occupy the circumference of a circle, the circle must contain an integer number of the wavelength, this lambda. And if so, then we can write the 2 pi r is equal to n lambda, where this r is the radius of this circle and n is an integer. But we know that lambda is equal to h by mv, so one can write 2 pi r is equal to n into h by mv, or we can say that mvr is equal to n h by 2 pi. So this mvr actually is this is basically the angular momentum of the electron regarded as particle. Hence the angular momentum is equal to the integral multiple of h by 2 pi. So this is basically actually the Bohr's postulate. So now we'll be move to the part 2. It contains the wave mechanics, postulates of wave mechanics, Schrödinger equations, the time dependent form, and properties of the wave function. So the main basics postulates of the wave mechanics is that first is the each dynamic variable related to motion of the particle can be presented by a linear operator. So actually in the development of wave mechanics, these certain postulates are developed, and these are the basically the fundamental importance, and out of those fundamental importance, the first postulate is the very crucial and very one of the fundamental importance, because that here it can give the how to define that operator. And so if we explain it the classical concept, that we know that in classical physics, and the certain definite function of the suitable variable are associated with the each observable quantity. So like we define that x, y and z, that if we write x, y and z, so writing x, y, z, these are basically associated with basically the position. So, similar way that if we say that momentum, that mv, this is associated with the momentum, and half of mv square, this is associated with the kinetic energy, and so on. So similarly in wave mechanics and quantum mechanics, the certain operators are associated with observable quantity. For the x component of linear momentum of a particle which has a classical representation like px is equal to m dx divided by dt, we have a quantum mechanical operator of this, like it is basically minus I h by 2 pi del x. So in if we write this in vector form, so this can be write as minus I h by 2 pi within bracket and operator delta. So similarly for the angular momentum, we know the angular momentum formula is that angular momentum is defined as that r cross p. So basically if we define as that angular momentum is r cross p, we can write that is p, we know this in representing as in vector form, so minus I h by 2 pi r cross delta. So similarly the kinetic energy p square by 2m, this we can use this p square, this operator, this we can use this p value, so this square multiply with the delta square and then divide. So if we simplify this, we can get minus h square divided by 8 pi square m whole into del square. So similarly if we want to the total energy, we know the total energy is equal to kinetic energy plus potential energy. So here we know our kinetic energy is half of mv square, or we can write p square by 2m plus potential energy, let's say ep, and this energy we have defined already with this, so one can write the energy operator in total energy in quantum mechanics, we can write in this way. So these are the expression for different operators, the quantum operator for several physical quantity. So second postulate is basically the states that the a linear eigenvalue equation can be always linked with each operator. Like suppose the total energy, we know that total energy operator is I is energy operator I is basically h by 2 pi into del t. So it will be always the eigenvalue equation for energy, it will be nothing but del psi by dt is equal to E psi. So here this psi is called the eigenfunction of the operator, and this term is called the E is called the corresponding energy eigenvalue, and this operator of energy is basically I h square by 2. And now coming to the third postulate state that when a measurement of dynamic quantity, suppose let's say a is made on a particle, suppose a quantity a is made on a particle for which the wave function is psi, we get the different values of a duration, different value of during the different trials, This is an conformity with the uncertainty principle. So basically it like that we can write that is A, this is basically equal to 0 to infinity psi star A psi dv. Here this operator A, and in the head this arrow mark is the operator associated with the quantity A. Psi star is basically psi star is the complex conjugate of psi, and the quantity this A is called the expectation value of operator A, that is the value of A obtained in the majority of trials. So the expectation value of momentum and energy may be found using the differential operator, like we can just erase it. That the most probable value of A is given by this. A is equal to 0 to infinity psi star A decker psi d dv, and the P will be is here will be denoted by this, that that integration is minus infinity to plus psi star, and within bracket minus I h by 2 pi delta psi, and this is 3 dimension del x del y dz, or we can once can write the delta v. So similarly that expectation value of energy operator can be defined as this is basically the energy operator psi star energy operator psi, and then dx dy and dz. So now will we move back that this is the linear eigenvalue equation can be always linked with each operator as we discussed. This is the postulates too. So now we will be move on the Schrodinger equation, and here we will be discussing on the time dependent Schrodinger equation. So basically the quantity that characteristics the de Broglie wavelength is called the wave function, and it is the main foundation of quantum mechanics, we know, and it also describes the stationary states and predicts energy levels of quantum systems. So if we denote, let us assume that psi is the our wave function in specify x direction, then we can write that psi is equal to a e to the power I omega t minus x by v. So if now nu is the frequency, suppose nu is the frequency, then we can write that omega is equal to this omega we can write as 2 pi and nu, and also we know that nu is equal to v lambda, then we can rewrite this psi value as this a e to the power minus 2 pi I then bracket Vt minus x by lambda. So now let E, the total energy E, and momentum P of a particle, then we know that E is equal to h nu E is equal to h nu, and we know that wavelength lambda and the momentum p is related with lambda is equal to h by p. Then if we substitute this value in this equation, suppose let's say this equation 2 and this is equation 1, then one can get psi is equal to a e to the power minus 2 pi I by h within bracket et minus px. So this equation 3 is actually is the mathematical description of wave equivalent of an unrestricted particle of total energy E and momentum p moving in the x direction. So now if we do the differentiation of this equation 3, if we do the with respect to x, then one can write that del psi by del x. If we do the two time of derivative del square x by dx square, one can write minus 4 pi square p square by a square into psi. Because here we are doing the derivative with respect to x, so this et term will be, there will be no component from this e part, and once can get, or we can write this differentiating two times del square psi by dx square is equal to minus 4 pi square p square by h square into psi. So this is our equation number 4. Now if we differentiating this equation 3 with respect to t, so if we now differentiate this with respect to only t, then we can write del psi by del t is equal to minus 2 pi I, because this is the x, so we are doing the differentiation with respect to t, so only this part will be here. So 2 pi I e by h into psi. So basically this is the del psi by del t equal to minus 2 pi I e by h into psi. So this is our equation 5. So at a speed small compared to that of light, the total energy the total energy of the system is basically sum of the kinetic energy and the potential energy. So basically if we want to describe this energy, so it will be in the form of total energy can be derived as p square by 2m. So let us erase this part. So basically the energy, we can write this p square by 2m, p square by 2m plus v, and this v is the potential energy, and in v is in general a position function of position, and v generally function of position and the time. So total energy is, now if we multiply this so this is our equation 1, this is 2, 3, 4, and this is the 5, and this is the equation 6. Now if we multiply both this equation 6 with the psi, we can once can get that E psi is equal to p square psi by 2m plus v psi. So now if we look the equation 5 and 4, we can see that E psi is equal to minus, if we look at that equation 4 and 5, these two equation, this 4 and this 5, so we can see that E psi is equal to minus h by 2 pi I and then del psi by del t. So this is nothing but this, and p square psi is equal to h square minus h square by 4 pi square del square psi by del x square. So now if we substituting this, so let us see, this is our equation 7 and this is our equation 8. Substituting this expression with the equation 7, we can get this equation minus h by 2 pi I del psi by del t. So let us remove this part. So this is equal to minus a square by 4 pi square m del square psi by del x square plus v psi, and ih by 2 pi del psi by del t is equal to this. So this equation 10 is basically, this equation basically called the time dependent form of Schrödinger equation. Why time dependent? Because here we can see that this penter is depends on this time. So if we express this in three dimensions, so basically this will be nothing but like ih by 2 pi del psi by del t. This is basically minus h square by 8 pi square m and then del square psi by del x square plus del square psi by del y square plus del square psi by del z square plus v psi. So this is basically the three-dimension time dependent form of Schrödinger equation. So now we'll be just look on Schrödinger equation on steady state. So we know that psi is equal to a e to the power minus 2 pi I by h et minus px, and if we break it in two components, then one can write a e to the power minus this component with the et, and once again multiply with this part with the px, and so this constant factor let us assume as psi naught. So one can write psi naught e to the power minus 2 pi I e divided by h into 2. So basically why we do this steady state form, basically that in a many situations the potential energy of a particle does not depend upon the time explicitly. So the basically the force that act upon it, and hence the potential v vary with the position of the particle only. And when this is true, the Schrödinger equation may be simplified by removing all with removing the reference to the t. So one dimension wave function psi, therefore we can write in unrestricted particle may be written in the form of this, and then this we can define that psi is this. So basically the psi is the, you can say here, the product of the position dependent function psi naught and a time dependent function of e to the power minus 2 pi I et by h into t. So now let us say, suppose this is our equation 1. Then if we differentiate this one, del psi by del t, one can get that this factor into psi naught and in this. So let's say this is the equation 2. So now if we again differentiate this with respect to, if we differentiate this with respect to x, then we can get del square psi by del x square is equal to this factor. So let's say this is our equation 4. So we can substitute these values in the time dependent form of Schrodinger equations. So time independent, we know the Schrodinger equation is the IH by 2 pi del psi by del t is equal to minus h square by 8 pi square m del square psi by del x square plus v psi. So if we use this equation and substitute these values of equation 2 and equation 3, one can get this equations. So if we now substitute and then reformulate this formula, so one can easily get this formula, del square psi naught divided by del x square plus 8 pi square m by h square e minus v psi naught equal to 0. So this is our equation 4. So now the this equation is actually called the steady state Schrodinger equation. Steady, or you can say the steady state form of Schrodinger equation. In 3 dimension, one can write, this is in only one component, so one can write del square psi naught plus this is the same 8 pi square m by h square e minus v psi naught is equal to 0. So usually it is written in the form of actually this del square psi plus 8 pi square m divided by h square e minus v psi is equal to 0. So now will we look on the properties of the wave function. So basically the probability that a particle will be found at a given place in space at a given instant of time is characteristics by the function of psi, that is nothing but we can write the function of position and time, and position also in 3 direction x, y and z. It is called the wave function. This function can be either a real quantity or it can be as complex quantity. The only quantity having a physical meaning that with the square of the magnitude, that is p is equal to psi square, that basically it is p is equal to psi square is nothing but psi into psi star. So we know psi is the wave function and psi star is the complex conjugate of psi, and the quantity p is have a name like probability density. The probability of finding a particle in a given volume, say delta x, delta y, dx, dy and dz is psi square dx dy into z. So it is basically psi square, this probability p will be is equal to psi square dx dy and dz. So further, since the particle is certainly to be found somewhere in the space. So one can write that this probability is integration with psi square, since dx dy and dz3 is there, so integration is 3 is equal to 1. So this triple integral extending over all possible values of this triple integration, basically this is for extending over all possible values of x, y and z, and the wave function psi satisfying the relation is called the normalized wave function. So next we are coming the orthogonal and normalized wave function. So if the product of the suppose two wave function is one wave function is psi1x, another wave function is psi2x. So now if the product of function psi1x and the complex conjugate of psi2, that means psi2 star x of psi2 star x vanishes when integrated with respect to x over an interval of defined interval. Suppose let's say x value is a to b, that is if integration of a to b psi2 star x psi1 x dx is equal to 0. So this psi1 x and psi2 x then said to be orthogonal in an interval of a and b. So so basically that if in a system have two wave functions psi1 x and psi2 x, and if the product of psi1 x and the complex conjugate of psi2 x with an interval limit of a to b is equal to 0, then the wave function itself psi1 and psi2 will be said to be orthogonal. So actually we know that the probability of finding in a particle in a volume element dv is given by we know that psi star dv. So the total probability of finding a particle in an entire space, of course, will be unity. So that means this is 1. So that it must be a well behaved, that is single valued and continuous everywhere. Like now if we say the continuous psi1x psi2x dot dot psi nx are solution of Schrodinger equation, then the linear combination psi x is psi s a psi1 plus a psi2, then a n sin must be a solution. The wave function must be approaches 0 as x tends to infinity. So this probability interpretation of wave function, so this is, we know that this is the Schrodinger wave equation. So first is the probability, defining the probability density. Second is the its normalization, that we know psi star psi dv is equal to 1, superposition and the measurement. So basically probability density is defined, that probability density basically define the with the square of the magnitude of wave function, that is basically psi square, and represent the probability density to finding the particle at a given point in space. Normalization, the wave function must be normalized, that is psi square over all space must be that psi square over all pets if it is dv is equal to 1, this value, this ensuring that the probability of finding the particle somewhere in the space is 100%. And third is the superposition, that means A particle can exist in a superposition of state. It can exist as a superposition of state, meaning that it can be a multiple state simultaneously. The wave function describes these superpositions. And last one is the that when a measurement is made of a particle, the wave function collapse, meaning that the particle is found to a specific shape, and the probability determined by the probability will be determined only by the psi square. So now we'll be looking on eigenfunction and the eigen values. So basically the Schrödinger time independent equation is an example of a type of differential equation that we have seen is called the eigenvalue equation. In general, we can write this eigenvalue operator as f operator any, and then psi is equal to f psi. So this differential operator is FOP, operates of a function phi, and this yields a constant f time, this f time times the function. The differential the function psi is called the eigenfunction of the operator OF, and the corresponding value of f, this is called the eigen. This is basically the corresponding value for f is called the eigenvalue. So basically these few parameters of this wave function, like that first is the psi square over all possible pace, and in time that psi square del x del y and del z is equal to 1. So this is the first, and second is the its orthogonal property, and then the normalization, that psi square dv is equal to 1. And if we say that we have a combination of a number of functions psi 1 psi 2 x then psi n x, then we can say the solution psi x can be as psi x can be as a1 psi 1 x plus a2 psi 2 x plus dot dot an psi n x. This is the combined solution of the wave equations, and the wave function must approaches 0 if this x value is tends to infinity. And the last one is the FOP psi is equal to f psi. So these are the main features of the wave functions.